In this video, we're going to be talking about operators in quantum mechanics. In quantum mechanics, an operator is a mathematical rule that tells us that if we have some state vector, right? Remember, we can denote this by this ket symbol of this psi. Or it can have any meaning in here. We can just call it psi. If you don't know what this means, then you have to go back and watch the previous video on Dirac notation. So the operator, as I said, is a mathematical rule that acts on some state vector, and it has this hat on top of it. In this case, I'm just going to call my operator A hat. And when it acts on this state vector, it will give us some other state vector. That is the basic principle. And this is how it acts on a ket. And if we have a bra, it acts like this. And basically this tells us that we have to write if it's a ket, we write it in front of it. If it's a bra, we write it afterwards. Okay, that's the order in which they have to operate. And that is given the nature of each of these mathematical forms. And I will get into that a little bit later. So just to make it clear, what are a few examples of operators? You have certainly seen some of these. So for example, the most obvious one is the case of the identity operator, which doesn't do anything. So if you apply this to some state vector, you get the same state vector. That's a unity operator. It's not particularly interesting. There's also the gradient operator, for example. Right, this one gives you the partial derivatives in each direction. Then you have, for example, the linear momentum operator, which we have seen before. And this one, as you might remember, is just minus I h bar times this nabla operator times psi, this ket psi, which will depend on the coordinates, of course. These are just a few examples of the different operators that we might encounter. Something that is very, very important in quantum mechanics is to know how operators relate to each other. In particular, what happens if we apply one operator after another. This is usually expressed by some mathematical product. So for example, if we have operators A and B, when they multiply, it's basically we are going to have A acting on B, which is going to be acting on some state. Now, something that is important to note is that it is not necessarily the same to apply B and then A than to do it, the other way around. So if we have some state function and we want to apply B and then A, it is not the same as to apply A and then B. What this means, and what we call this, is that we say that these operators in general do not commute. They can commute. These two can be equivalent, but in general, they are not. And in the next video, we're going to be talking more about the commutators. So if you have never heard of that, don't worry, because we will take a look at that, and in fact, quite a bit. Some rules that apply when dealing with operators is that first, there is association. So if we have three operators that are going to be acting, we can just take one operator acting on another and then relate it to A, or we can just let A act on B and then have it act on C. That's okay. That's going to be the same. Then, well, just to make it very clear, the order is important. So in case it wasn't clear when I said it there, if we have A acting on B acting on some state vector psi, this is not necessarily the same than to have this. Okay, that's very, very important. And another thing, if we have this same situation, A acting on B acting on some vector psi, what you can do is take first B, and this is actually the way that we do it. Usually just B acting on psi. Okay, so that is, whoops, I accidentally muted my microphone there, sorry. Okay, so now what we want to do with operators, and that's going to be the case very often, is we want to determine what we call the expectation value. And the expectation value will have a very particular form that we will get to in a minute. So in order to get to that point, we first want to take a look at what happens if we have a bra, and then we have some operator, and then we have some ket that is not necessarily related to the bra. So for example, this situation. Now this is going to give us some complex number. Now, how do we know this? Well, remember, if this A acts either on psi or on psi or on phi, we're going to get some other vector. So in the end, this is going to be just the inner product between these phi and psi vectors. Okay, so that's why we're going to get a complex number, because that's what we get in the case for these inner products. And you have to see what this operator does in order to know exactly what the result is going to be. And as I said, in this case, it doesn't really matter if you take this part first or this part first with the operator, you're going to get the same. Now, in quantum mechanics, we're going to be dealing particularly with a kind of operator that is called a linear operator. Now, this does mean basically that it behaves the way we are kind of used to have things behave, because at least in physics, we really like it when things are linear. So what that means, for example, is that if we have this operator A and it's acting on some complex number A1 times some ket plus some other complex number A2 times some ket, what we're going to get here is just distribute this operator. So we get the A1, which is just a constant, times the operator A acting on psi1 plus A2 A acting on psi2. So this is basically the way that we would expect it to, and obviously this is going to be the same if we have some bra psi1 A1 plus some bra psi2 A2, and we have the operator A acting on it. So in this case, it's going to be the same. So we get this constant A1, which we can write in front, times the bra psi1 and the vector A acting on it, plus constant A2, times the bra psi2 and the vector the operator A acting on it. So that's the way that we deal with that. Now there are some more things that we want to take a look at here. Particularly now, as I had said, we want to determine the expectation values for our operators, because the expectation values, as we have seen, they can basically tell us what we expect to find in some experiment, what we can determine experimentally. So if we have some expectation value, which we now write like this, we have written like that before, but now you can see that this is kind of the abbreviation of this bracket notation. That's why I like, at least that's how I see it. This expectation value is then going to be the bra of some state psi, which can be, for example, the wave function of the hydrogen atom, or the wave function of a particle in a square well, or whatever system we are dealing with. And then we sandwich inside our operator. And it's very important, this is divided by the inner product of psi with itself. And if this state psi, if the ket psi is normalized, then this is just 1, and all that we have to deal with is this. That's why it's always so nice when the physical states are normalized, because then we don't have to take this part. Okay, another thing that's interesting to note is that the quantity bra of some phi times, I meant to put up psi in there, times, the ket phi bra psi, this is actually a linear operator. It's just in Dirac notation. And just to show it briefly, let's have this act on some ket psi prime, for example. Now, if we have this, this right here is just What is it? This is just a complex number. This is an inner product. So we can actually write it in front, and that's very important to notice. You have to notice that if we have a bra and a ket right next to each other with nothing in between, that's just an inner product. This is a number. So we can just put it down in front because this is a constant. So we can just write it like this. And then we have our ket phi. So this operator basically took our psi prime and it gave us some number times this phi. Okay, obviously what exactly it is, it will depend on what our bras and kets, phi and psi are. But you know, in general, it is just so you know that this exists, because this will pop up every now and then. So it is good to know. For now, I'm not really going to use the part of using discrete bases here in quantum mechanics, because what we're going to do in the future, which is dealing with angular momentum and spin, there isn't all that much use just yet. So I will introduce more of that when we need it, because I don't want to introduce it too soon. Otherwise, I feel it's harder to understand because you don't really know what it is for. So I'm going to try to give you everything as we are needing it. And just as we saw in the last video, there are a few things that don't make sense. For example, we can't have some ket and have the operator on the right side. That doesn't make sense. That's not good. And similarly, we can't have the operator on the left side of a bra. That doesn't make sense either. Okay? And that's similar to how in the previous video I told us that some things don't make sense. For example, to have these two kets together, or to have two bras together. And I think I forgot to tell you the reason. That is because these right here are going to be just column vectors. These here are row vectors, so these multiplications don't make sense. You can't multiply two column vectors, you can't multiply two row vectors. Okay? That's the reason behind that. Now, the next thing that we need to discuss is the concept of the Hermitian adjoint. The Hermitian adjoint. This is also called the Hermitian conjugate. We usually write this as a dagger. Okay, so the Hermitian adjoint or conjugate of some complex number a, right? That's going to be a dagger. This is the conjugate or adjoint. This is just the original complex number. Now, what this is going to be, this is an operation that we take that is basically the same that we saw before when we conjugated some number, except that if we want to do it to an operator, it isn't as simple. It is not complicated, but it is not quite as simple as just putting a minus sign in front of every complex number. So the adjoint of some operator A is going to be a dagger, of course. And how we can define some operation, for example, let's say that we have, just to make sure that we show like everything in one go, we have some bra psi, we have some operator A, and we have a ket phi. And let's say that we want to take the conjugate or the adjoint of this entire thing. So to do that, there are three things that we have to take into consideration. Okay, there are three steps. First of all, we need to replace constants by their conjugate, So basically, if we have some alpha, we now need to have the conjugate, right? If we had, for example, 2i, now we need to have minus 2i. That part is simple, and that is probably not new. The second step is to replace kets with their respective bra, and also replace the bras with their kets. Okay, so that's very, very important. That's step number 2. And step number 3 is going to be to replace operators by their adjoints. And remember the adjoint is going to be, we have to take the complex conjugate of this operator itself, and we also have to transpose it. Okay, so take adjoint of the operator. Those are the three steps. So if we apply these right here, we're going to get, well, there is no constant here, so that's not really important. Now this ket is now bra, then we have the operator but with the adjoint, and then we have the ket of psi, right? So that's the way to do it there. Now let's just take a few, see a few things about this. So if we have some operator A and we apply this adjoint to it, we take its adjoint, and then we do it again, we are going to end up with the original A, right? Because we have transposed it twice, so we get back to the same, and we also have applied the complex conjugation to each one of the complex numbers, so we did it twice, so we get to the same thing. If we have some complex number A times some operator A, and we want to do the adjoint to all of that, we're just going to get complex conjugate of A times this adjoint of the operator A. If we have some sum of operators and we want to take the adjoint of this, then this is simply a matter of taking the adjoint of each one of these operators. If we have some product of operators and we want to take the adjoint of this, then we have to reverse the order and replace each one of these by their respective adjoints. Okay? And that is basically the first thing. Now, something that we have to note here is what happens if we have some sort of number inside of a bra and a ket. So for example, if we have some constant A times operator A acting on psi, now this is something that we have discussed previously. I just want to give us a quick reminder of this because it is important, and I'm going to use it in just a bit. So if we have some constant times the operator times this psi, this is the same as putting the constant outside, because remember that this is basically a vector. I mean, there's several representations, but it could be a vector or a function, and multiplying the constant by the function, you can just write it outside. But the operator can also go outside, so the operator part is new. That's why I wanted to show us this. The operator part, we can just take it outside of the vector in the notation. Okay, that's very important. And most important is what comes now, because this is intuitive, I guess. It's not too difficult, but the case of the bra can be more complicated. So if we have, for example, some complex number A, operator big A acting on this psi bra, if we want to just isolate this bra, we can take this number out, but remember we have to take the complex conjugate of the number. We saw that in a previous video, and you cannot forget that. And the second thing is that you can take this operator outside, but you cannot put it in here. It has to go to the right of the bra. Remember, it doesn't make sense if you put it in here. That's not good. You can't do that. Okay, so that is something that I wanted to comment. That's very important. And for this reason, and why is this relevant at all? That's relevant because if we have a situation like this, so say we have the sandwich of bra of psi, operator A, ket of some other the state vector psi, phi, this is the same as having the adjoint of A acting on psi, and then just the ket of phi, or to write it as the bra of psi, and then have the operator act on phi first. Right, so those are the ways to see about it. So it's basically have it act on this first or have it act on the other one first. That's basically the difference here. And although I did mention it briefly before, I wanted to make sure that I remind us of it quickly. So this part is mostly done. There is one last thing that I want us to consider, and it is what happens in a particular case, which are what we call the Hermitian and the anti-Hermitian, or also called skew Hermitian operators. So if we have an operator that satisfies the following things. So if we have the operator and we take its adjoint and we get the same operator, then this is what we call Hermitian. And if we have some operator and we take its adjoint and we get back minus this operator, this is what we call anti-Hermitian or skew Hermitian. And this is just extremely important. Why is that? It is because the Hermitian operators are going to be what represent what we call observables. So the things that we can measure are going to appear in quantum mechanics as Hermitian operators. If the operator is not Hermitian, then it is not going to be observable. That's extremely interesting, and we will talk about it much more when we are actually dealing with spin and angular momentum. So for now, this is just a quick heads up of what is coming. Now, I do want to show us quickly that the expectation value of a Hermitian operator is real, and that the expectation value of a skew Hermitian operator is going to be imaginary. So in order to do that, let us take just the sandwich of some expectation value. Remember, expectation value will be brat of some psi times some operator times this ket. Now let us then conjugate this, which will mean obviously to take the Hermitian adjoint of this operator later. So if we take its conjugate, we have to change bras for kets and kets for bras, but these two are the same, so we're still going to get psi here, then the Hermitian adjoint of the operator times psi here. But take a look at this. This right here is, as I said, the adjoint of this operator. But if the operator is Hermitian, that means that this is going to be the same as the original A. All right, so what does that mean? So if that is the case, then we have that, and remember, this is a number. The expectation value is some complex number in general. And we have that the conjugate of a number is the same number. The only way that that happens is if the imaginary part is 0. Or that means that this is real. So it's a very straightforward proof, because all we had to do was conjugate this. We got that this right here is going to be the Hermitian adjoint of the operator, and because it's Hermitian, it's the same as A, so we get that the conjugate of a number has to be the same as that same number, and that means it has to be real number. Let us now take a look at what happens if we do the same thing but with a anti or skew Hermitian operator. So let's conjugate this. Once again, we take the kets of bras of kets, and this time when we take this adjoint, it is not Hermitian, it is skew Hermitian, which means that the adjoint is going to be minus this operator. So this means we're going to get minus the same number that we had previously. And what sort of number, if you take its conjugate, is going to be negative of that original number? Well, that's going to be a purely imaginary number. So that's how we can tell that the expectation values of Hermitian operators are real and the expectation values of skew Hermitian operators are going to be purely imaginary numbers. Now, the final thing that I want to introduce, and that's actually going to be the main thing that we will focus on during our visit to angular momentum and spin, are going to be the search for eigenvalues and eigenvectors of operators. So I hope that you have seen in some linear algebra courses the concept of eigenvalues and eigenvectors. And in this case, we want to find them for operators. What basically this means is that if we have some state vector, psi, as we have dealt with before, then, and we are going to have some operator acting on it, right? And if this procedure gives us some complex number multiplied by the same state vector, then we are going to say that this state vector is an eigenvector of A with eigenvalue small a. Okay, this only happens if you take the operator, let it act on some state vector, and then you get some multiple of that same state vector. If that happens, then you will find, then this will be, the number will be the eigenvalue, the vector will be the eigenvector. And this is going to be extremely important in what we'll do in the future. And its meaning I will explain a bit more when we're dealing with commutators, because, well, I can't really say it for now since we haven't seen them, but it's going to be very important. So I will see you in the next video where we'll be dealing with commutators.